Okay, so hi everybody. Today I want to start talking about the field of what's called wave optics. And these are situations where we cannot ignore the fact that light is an electromagnetic wave. When we've talked about lenses and mirrors thus far, we've just been able to think about the light as stuff that follows straight lines from a source to a receiver, unless you pass it through a material so its trajectory gets bent or it bounces off a mirror. That works for quite a few applications, but there are also situations where we can't ignore the wave nature of light. And one of the ones that shows that most clearly are situations where you have what's called interference. And this is an important concept in modern optical technologies and various other situations. And it's something very key to the behavior of waves that you may have already encountered. And what I want to do is illustrate this concept with what I think is the most straightforward system to do it with. And this isn't something covered explicitly in the textbooks so much, but I think it's one that makes the concept of interference a little bit more straightforward. The specific system we're going to consider consists of partial mirrors. The specific thing we're going to consider is basically a mirror that when you shine light on it, half the light gets reflected back, half the light just gets through. And when I say half the light, I mean half the intensity. Half of the intensity, energy, etc., is reflected off the surface, half of it keeps going. You can make these things. Like, you know, when you look, say, at a piece of glass, some of the light gets through, some of the light is reflected. So this is not an exotic object. It's just a normal piece of material. And the specific situation we want to consider is, what if we have two of these in a row that are parallel to each other? So we have one here and one here. Both have the property that when light hits them, half of it goes back, half of it goes through. In that situation, how much light comes out through both of these objects? And there's a couple of options here. Is it about a quarter of the incident light? Is it more than a quarter of the incident light? Is it less than a quarter of the incident light? Or do you not have enough information to figure that out? And I'd like you to think about that and pause the video to think about how you might answer that. Okay, the correct answer, this is one of the times where D, none of the above, is the right answer. And I want to try and explain why. So to see why, let's consider a diagram like this. What we're going to imagine is each of these steps here is a different step in what happens to the light. The light first comes in at some intensity. It hits this mirror, half of it gets bounced back, half of it goes forward. Fine. Then it encounters the second mirror. At this point, half the light goes back, half the light goes forward. Since this is half of a half, this is where you might get a quarter. So this amount, at this point, the amount of light leaving is about a quarter. But this light going back now hits mirror one. Half of that light keeps going and leaves the system the other way, but half of that light gets bounced back towards the second mirror, giving it another chance to make it through. So some fraction of the light that bounces back bounces off the first mirror and then gets through. So there's a second component to this signal out here. And of course there are more, but let's just stick with this. So we have one signal, and now we have a second signal. Now it would be very natural, and most people think this way, to say, oh, there's more light in some form, so the intensity is higher. So it's more than a quarter. But that's where the problem is coming. To really understand how the signals from these two particular waves combine, you need to understand that they are, in fact, waves. So let's look at that again. Imagine we could zoom in on these two signals. They're both electromagnetic waves where the electric field swings up and down, just to draw it in some way. And this one is the stronger one. This one is a weaker one. But what we see is not those two individual things. We see them on top of each other. We see the sum of their electric fields. Now, if the waves are like I drew them here, where everywhere this one points up, this one points up, and everywhere where this one points down, this one points down, then these two waves add together. The total electric field is the sum of the two electric fields, and you get a bigger electric field, you get a higher intensity. That kind of is what many people go to, and that's a possibility. When the two waves interact like this is what is called constructive interference. Interference generically just means the summation of two different electromagnetic waves, okay? And it only really does things when the two waves are more or less heading in the same direction. Okay, but this isn't the only possibility. That other wave could be going like this. It could be pointing down when this wave points up, and vice versa. When this one's pointing down, this one points up. Now, when we add this electric field to this electric field, the total electric field is less than this. The total electric field of these two has a partial cancellation, which reduces the total electric field and reduces the intensity of the light. So in this case, having both of these waves on top of each other reduces the intensity. This is what is called destructive interference. It's where two electric fields of two different waves start to cancel each other out. So both are a possibility. Which one happens? Well, the answer to that depends on how far the second light ray, how far this second wave had to travel. Remember, this wave is from the light that just went straight through. But this wave came from a signal that bounced off this mirror, went off here, and went here. It went an extra distance that's twice the distance between the two mirrors. That extra distance means that it might be some way, it is some distance behind. And the question is, how many wavelengths is it behind? If this to here to this to here was one wavelength, then these two things would be in sync. This would be high and this one would be high when this one was high, because basically there's just an extra wavelength this wave traveled. That also works if this distance is 2 times the wavelength, 3 times the wavelength, 4 times the wavelength. As long as it's a whole number times the wavelength, you will get the two signals in sync, or more generically in phase, and you will get constructive interference. So the condition for constructive interference is the extra distance traveled by one of those bits of light, 2D, equals lambda, the wavelength of the light, times m, where m is an integer, 1, 2, 3, 4, 5, it can be 72, 396, it doesn't matter. As long as it's an integer, you get constructive interference. Now, on the other hand, if this wave traveled half a wavelength or 1.5 wavelengths to bounce back and forth once, then when the electric field here is positive, the electric field here is negative. Then they're out of phase. They're exactly out of sync, and they'll cancel out. So the cancellation happens when this distance 2D is the wavelength times m plus 1/2, where m is again an integer. It can be 20.5, it could be 81.5, it could be any of those. As long as it's close to an integer plus a half, you will get destructive interference. So what matters is not necessarily how big D is, it's how close the fractional part of 2D over lambda is to 0 or a half. If you have this, if basically 2D is really close to an integer times lambda, then you will get strong constructive interference. If it's close, if it's just half a wavelength longer, you get a strong destructive interference. This is what matters. Now, this means that the strength of the signal you get out is really sensitive to this exact value of the distance. You know, even if this distance is, say, a millimeter or a meter or something long, if you change this distance by a fraction of a wavelength, it will affect the intensity. This means this is a really good way to measure changes in distance. And in fact, it's this technology that was used to make extremely sensitive measurements of position in gravity wave detectors like the one in Hanford, which was able to see signals from black holes spiraling into each other, you know, in other galaxies. So this is a powerful technique. But there's another aspect to it that's important. It's that it's wavelength dependent. So for example, I can ask, if, just to give a sense of how this sort of thing works, if we were using light with a wavelength of 500 nanometers and D was something like about a millimeter, what kind of interference would you get? Would you get constructive or destructive? Try it. Figure out what you get. Well, calculate it. 2D is 2 millimeters. Lambda is 500 nanometers. Divide those two from each other, you get 4,000 even. That's an integer. So you would get constructive interference. By contrast, what would happen though if instead of sending in light with a wavelength of 500 nanometers, you send through light with a wavelength of 450 nanometers? Keep the distance the same. What happens in this case? Well, in this case, we have our distance, 2D, is still 2 millimeters, but now we have to divide by 450 instead of 500. And in that case, you don't get a whole number. You get 4666.6 repetent. Now, that's not 0.5, but it's closer to 0.5 than 0, so you get destructive interference. Things like this really care about wavelength. And the thing is, this isn't something exotic that only happens with perfect things. This happens all the time, especially in thin sheets of material. Like if you bounce light off of a membrane, like say a soap bubble, some of that light, as you know, gets reflected. Some of it gets refracted into the material, then can bounce off the other surface and get refracted out. This, again, gives an extra path length to the light. So you can have this light and this light constructively or destructively interfere. And whether they do that or not depends on both the thickness of the bubble, the angle, but also the wavelength. This is why things like soap bubbles or oil slicks or even CDs show rainbows on them because at different places they have different thicknesses and you're looking at them at different angles. So this happens all the time. So that's the concept. The thing is, we also want to try and show you how to use this practically in places where you can actually calculate things. And the classic place to do that is what is called a double slit setup. You send an electromagnetic wave onto a wall with a pair of slits, very narrow slits that let the light through. Now, we'll talk about this next time, but the light coming through each of those slits starts to spread out. So effectively, you have two sources of light where the electromagnetic waves are in phase with each other when they right at these two locations. And then the light spreads out and approaches the surface. There are various cute visualizations like this of what the waves do in between, but if you hold up a sheet of paper here, you don't just see a lot of light here and then it gradually fall off. You also see the brightness periodically goes up and down. This is another example of interference. In this case, what's happening is you have light coming from one slit and the other slit. And they're traveling some distance to reach this point. In some locations, they're traveling slightly different distances. And sometimes that different distance means that this wave is a little bit behind or ahead. If the distance is such that the two waves are exactly out of phase when they hit this point, they cancel each other out and you don't see much light. That produces a dark feature. At other distances, at other locations, the distances traveled by these two beams of light are such that the waves are almost in sync. And so you get more light than you'd expect. You get a bright feature. Now, doing the geometry of this properly requires a bunch of approximations and things that I don't want to get too far into. But effectively, for a lot of these sorts of problems, it's the same logic. The distance, the extra distance traveled by, say, this wave is given by this parameter, d, the separation between the two slits, times the sine of this angle theta. When that difference in the distance is an integer times the wavelength, so it's 0, plus or minus 1, plus or minus 2, etc., you get constructive interference. You get a bright signal. And that's what you see here. Each one of these bright features corresponds to one particular value of m. The one in the middle is m equals 0. The two waves travel the same distance. This is m equals 1, m equals 2. This is m equals minus 1, m equals minus 2. And which one's which, I'm not going to pretend to know off the top of my head. But that's basically what's happening here. The dark patches, by contrast, are places where this distance, d sine theta, again, as you make theta bigger, you go further up this or further down. And if you make theta negative, you go further down. Any place where d sine theta equals an integer plus a half times lambda, you get dark bands. And you can make these bands very dark because these two waves are nearly the same strength. So whereas before one was strong and one was weak, in this case they're both equally strong. So when they cancel, they can almost cancel out completely, making a very dark region. Practice doing that is sometimes kind of hard, so you get slightly blurry patterns. Now, again, this depends on wavelength. And again, it's because it's how many wavelengths are involved get into creating this. So the pattern you get not only depends on what you look at, what the distance is, it also depends on what wavelength of light you use. So another concept problem to consider. Say we shine shown a red light through this thing and got this fringe pattern. So here are places where there's constructive interference, and the dark bands are where there's destructive interference. Now we're going to use the same setup with the same separation, but now send blue light through. Where do you expect to see a band? Do you expect to see a band here, right on top where the red band was? That would be option B. You expect it to be further out? That's option A. You expect it to be closer in? That's option C. I'd ask you to pause the video and consider which one you believe. The correct answer turns out to be C. The thing is, if we go to blue light like this, the wavelength gets smaller. So to produce constructive interference, you need this thing to be smaller. Sine theta has to be smaller, which means that the separation between these bands has to get tighter. So what tends to happen is you get the red, when you send multicolors through, the red band ends up here, the blue band ends up here. This process splits light into its component colors, just like a prism does. But this is doing it in a much more controlled way. And when people want to look at different colors of light nowadays, what they do is they use this process. But they don't use two slits, they use lots of slits. You take a surface and cut a bunch of gaps into it, regularly spaced by some distance d. What happens in this case is now you don't just have two signals to interfere with each other, you have a lot, and they all interfere with everyone else. Now, it turns out that this condition still works. You still get constructive interference when d sine theta is an integer times lambda. But what starts to happen is you get destructive interference almost everywhere else. In two slits, when you're not quite at that condition, it's not too far off. But if you have lots of slits, then the condition where everyone's constructively interfering transitions to a state where at least two of these are very badly destructively interfering. So what happens is you get strong signals only at very narrow, very specific angles. Everywhere else, you don't get much at all. And it's still the case, though, that different wavelengths go to different angles. And what you get is something that disperses light very well in an extremely controlled way. These are what are called diffraction gratings. They are basically designed to have a series of interfering patterns that disperse light, much like a prism does, but they can do it a lot more than a prism can over a broader range. But again, since it's the same basic idea, the red parts always get out at higher angles, and the bluer parts always get at lower angles. And this goes for any particular wavelength you do this with. You can do this in the ultraviolet, you can do it in the infrared, and this even happens in some natural systems, like say feathers and butterfly wings. It's part of how they develop their particular sheen and color. So hopefully this gives you a sense of what interference is and why it's important. And in the next video, I'll go through a couple of examples of how to do these sorts of problems. Thank you for your time and attention.